Okay, we wrap up now by tackling problems 21 through 24 on assignment 3. Number 21. FRX Bank is offering a mortgage rate of 7.25% per year. Assuming monthly payments are required, compute the effective annual interest rate the bank is charging. Well, we can go back and forth between the effective annual rate and the nominal rate using the formula we see here. The effective rate takes into account compounding. The nominal rate does not. And when banks quote interest rates on loans, they quote nominal rates. And what you actually do, and we did this in an earlier problem, you divide this by the number of periods per year. In this case, monthly payments, you divide that by 12, and that's the monthly rate you're being charged. But the effective annual rate would take into account compounding, and that's what this equation does. You can see the compounding with the exponent. We're going to raise this, we're going to take the monthly rate, add 1, and raise it to 12th power. We're going to take into account compounding. So with monthly compounding, M is 12. M is defined as the number of compounding periods per year. So take the 7.25% as a decimal, divide by 12, add 1, raise it to the 12th power, and then subtract 1. And we find that the effective annual rate is 7.5%. 22. If you deposit $100,000 into an account that pays 10% per year compounded continuously, how much will the account be worth 5 years from today? Okay, it's a simple future value, present value calculation. We've done this where we had 10% compounded annually, 10% compounded semi-annually, 10% compounded quarterly, and then 10% compounded monthly, but then we stopped. We could have compounded it daily, we could have compounded every second, every billionth of a second, or you can actually compound it continuously, which means you're compounding it every infinitesimal part of a second. And when we do that, we have to use this equation. Future value equal present value times e raised to the r times n power. So we take 100,000, which is the present value, we take the interest rate as a decimal, 0.10, multiply that by the number of years, which is 5. So it's e to the 0.5. So in your calculator, you're simply going to press 0.5. I think e to the x is a gold first, so gold e to the x, and then multiply by 100,000. When you press e to the 0.5, you get 1.6487. Multiply that by 100,000, and our future value is 164,872.13. And you can compare this answer to the one we did earlier, where we took $100,000 at 10% for 5 years, and we did annual, semi-annual, quarterly, then monthly. And you'll note that with continuous compounding, we'll get the greatest future value. This will be greater than the one we got in Part D with monthly compounding. 23. A company's sales grew from $150 million in 2007 to $300 million in 2012. At what rate have sales been growing? And then we'll answer the question, would it be correct to say that sales have been growing 20% a year? In other words, they doubled, so 100% increase from 150 million to 300 million. If it doubled in 5 years, is that 20% a year? We're going to see that it's not. And you might be wondering here, where did this problem come from? We didn't have any problem about growth rates. Well, sure we did, in disguise. This is simply the future value of a present value equation. Future value equal present value times 1 plus r to the n. Well, that's r, when you use the future value equal present value times 1 plus r to the n, r is the compound interest rate. In this case, G is the compound growth rate that makes a present value of sales grow to a future value of sales. So let's put in the 300. I'm going to knock off the millions. It's going to cancel out with the millions on the other side. So 300 million equal 150 million, or 300 equal 150, times 1 plus G to the 5th power. And this is a problem just like we'd solved for an unknown interest rate earlier, where we let 50 go to 100 over 10 years. Well, we're going to solve it algebraically just like that problem from the last video. If we divide both sides by 150 and then juxtapose the sides here, we'll get 1 plus G to the 5th is equal to 300 over 150, which is 2. Raise both sides to the 1/5 power, and we get 1 plus G is equal to 2 to the 1/5. Now subtract 1, and we get a growth rate of 14.87%. So if a firm's sales grow 14.87% per year for 5 years, that compounds to 100% growth over 5 years, not the 20%. Had it grown 20% per year, sales would have actually increased 149%, not 100%. Okay? So there's a compounding effect to growth that if you simply take 100% divide by 5 and say it's 20% a year, you're ignoring that compounding effect. Okay, our last problem, 24. Sally is 40 years old and will begin saving for retirement. She plans to save $1,000 a month at the end of each month until she retires. Assume she earns an annual return of 9% on her investments. She plans to retire at either age 65 or age 70. Okay, first let's calculate how much money Sally's going to have at 65, if she retires at 65. We're going to calculate the future value of an annuity. We have to do it on a monthly basis. So the interest rate is going to be 0.75% per month. She's going to save for 300 months, 25 years. She's now 40. She's going to save until she's 65. So she'll save 25 years, 12 months per year, 300 months. So put in $1,000 as the annuity. Don't forget to convert your interest rate as a percentage to a decimal. Calculate the future value and we get 1,121,121.94. How much will she have at age 70? Now we do the same thing except n's going to be 360. And we get a future value of 1,830,743.48. And as you'd expect there, she's going to have a lot more money if she works 30 years instead of 25 years. And it's worth pausing for a second. There's two reasons this is, 70% higher than you got in Part A when she only works 5 years more. Well, two things happen. Well, clearly she's going to have 5 more years of deposits, but all the previous deposits over the previous 25 years will continue to earn interest for 5 more years. And I would dare say that's the greater increase here than just the 5 more years of deposit. They both contribute to the larger future value. But I think the greater amount is this amount earning interest for 5 more years. And then on top of that, you've got the future value of the last 5 years of payments that would now go in. Okay, Sally expects to live until she's 85. If her investments continue to earn 9% per year after retirement, how much will she be able to withdraw at the end of each month after retirement at each retirement age? Okay, if she retires at age 65, now you're going to take the amount that she accumulated when she was 65 and spread it into an annuity over 240 months. Because if she retires at 65 and plans to live until 85, she's going to make 20 years or 240 months of withdrawals. We saw that if she retires at age 65, she would have this future value. Set that equal to an annuity times the present value of the annuity using the same interest rate. And she's withdrawing for 20 years or 240 months. And you'd get withdrawals of $10,087.03. She could withdraw that amount every month for the next 240 months, 20 years. If she retires at age 70, now she's going to have 180 months of withdrawals. Because if she retires at 70, now she only has 15 years over which to make the withdrawals, or 180 months, and she also has a higher future value that she can withdraw from. So we can see when we solve for A here, we get a much greater amount, almost double amount that she can withdraw each year. Not quite double, 80% higher, whatever it is, roughly, than she had before. Okay? All right, this ends our solutions to